All right, looks like we're working. Okay, so welcome back to the channel. I know it's been a while since I've made videos. There's a reason for that. I recently got into a PhD program. I moved across the states and I got a new house and I got 2 dogs. Other than that, it's been pretty laid back. Anyways, my apologies for any background noise. I got a dog walking around right now and he's not exactly the most discrete organism on the planet. And we are going to get back into my favorite stuff, physics. My PhD is in biophysics, and where I study membrane receptors, glutamate receptors in particular. But I also, again, have this deep interest in other areas of physics and hopefully being able to implement these areas into my own research. And I've decided this is going to be a little bit of a different structure now. So I'm going to put playlists on my website or on my YouTube channel. Each playlist is going to be dedicated to roughly one book. And I think that'll be a really good way for me to have a lot of good content to give you guys, to be well organized in the content that I give you guys, and to hopefully get input from you guys as to what books you would want me to cover in the future. And this is a quantum field theory. So as you know by the title of the playlist, we're going to be going over the first quantum field theory textbook that I think is very good. I've read through it. I've read through many quantum field theory textbooks. So I'm coming at this book. This is No Nonsense Quantum Field Theory by Jacob, I don't know how to pronounce the last name, Schwittenberg. I'm coming at this book from the perspective of other areas, other books, other quantum field theory textbooks that are out there. So that it's not like a complete black box, if you will, of tackling this book. Anyways, let's get right into it. You will be able to go onto my Patreon page that I will sort of fix up later, hopefully soon, so that anyone who wants to contribute to this channel will be able to ask about any specific topics they would want me to cover, and any specific books that they would want me to cover as well. And it doesn't have to be just physics. I've done a lot of reading in a lot of areas of physics. So it can be quantum field theory, it can be general relativity, when we'll be going over textbooks in general relativity. It can go over biophysics, it can go over cryo-EM or something like that. That's where I shine in my research. But anyways, enough about me. Let's get right into this. So this is going to roughly go chronologically from the table of contents. So we start off, so the table, in order to not infringe on any copyright issues on this book, I'm not going to display this like page by page. What I'm going to do is I'm going to sort of kind of just go through the sections and explain the section so that if you decide to go through this book, it'll be a lot easier for you to do so. But anyways, we start off with a bird's eye view of quantum field theory. And that starts on page 23 of the textbook. Right, so this is going to be a bird's eye view, of QFT. And I've gone through this already. Normally the introductions are, if you're new to this kind of stuff, it can be overwhelming, right? So he off the bat he gives equations that we'll come to later on. So I would recommend, if you're reading this book, maybe to skip through most of the bird's eye view of this textbook, because he'll go through it later. He'll go through it in more depth later. But I want to cover sort of the latter part of this bird's eye view of quantum field theory, because I think it'll be very useful to kick us off. And so he talks about fields. What is a field? What's a mathematical field? And we could sort of think of a field as this mathematical entity that permeates all of space and time, right? And we could think of it as like a grass field or something like a grass. So a grass field is a field that contains grass, right? Or you could think of any sort of field, and we can draw one. This is sort of the prototypical what a field might look like. You have peaks and troughs, and at every point on the field, you have some sort of object, some sort of value. It can be, and when we're speaking mathematically, these objects can be numbers. So we can have a number field, or what are called scalar fields. Scalar fields. We can, we would attach to each point a number, 5.68 or something like that. Right. We're merely just, we're permeating all of space and time with a field, and that field is going to be just a scalar field. There's going to be numbers everywhere. Some of them are going to be big numbers, some of them are going to be small numbers. Right. We could also have vector fields, right? This is where things get a little bit more interesting, right? Because a vector is something that has components to it. So we can have a vector here instead of, we can have vectors here instead of numbers, right? So if you've taken vector calculus before, a vector field is, you can sort of visualize vector fields in three dimensions. So you have an arrow at each point, and the arrow at each point sort of tells you what the magnitude of the field is there, but also what direction, say, a particle will move if it's located at that point in the field. We have Tensorfields. This is something that's not covered in this book, but as I said, I'm coming in from different perspectives and areas of physics, and I'm bringing these perspectives to all the books that I'm going to help you guys understand. Tensorfields. So let's give examples for some of these. So like a scalar field, an example would be temperature, right? So I can, you tell me at some point in this room, sort of point outside, in three-dimensional space, and you point to that point and you ask me what the temperature is, and I'll give you a number, 4 degrees Celsius or something, or 6 degrees Fahrenheit or something like that. So that's a scalar field. A vector field, an example of a vector field would be something like the electromagnetic field, right? So you have vectors located at every point in space that tell you what the magnitude of the field is, of the electric field is, and what direction a test particle will move if you put it at that location in the field. So this would be like the electromagnetic field. And the tensorfields are a little bit more complicated, but we'll see these in GR. General relativity. So more on the bird's eye view of quantum field theory. So he talks a little bit about fields, and he's going to talk more about fields in a later chapter. But he has this really good diagram on page 35. If you have the book with you, if you don't, it's totally fine. We're going to go through this even if you don't have the book. I'm going to try to make it refer to page numbers and stuff like that. But he has this good diagram. He has a good diagram. He says, okay, it says the following diagram summarizes our plan up to this point, and he talks about who are the actors, right? Who are the actors in this field, in these fields? We have scalar fields, we have vector fields, we have tensor fields. There's something else that we need to cover is a spinor field. These are going to help us describe electrons. And again, spinors are weird objects. We define each and every one of these objects, as how they transform, right? And I'll get into the nitty-gritty on that in a later video. But yes, so we have scalar fields, spinor fields, and vector fields. Those are the fields that we're going to be concerned with in primarily in QFT. So tensor fields, we're not going to cover that one. We will do that in GR course. But again, nothing's really stopping us from thinking up more mathematical objects that are, say, like covectors or twistors or something of that nature, where we will definitely want to entertain those notions, right? Covectors transform differently than vectors do. Twistors, again, those are weird things. From this, I believe Roger Penrose talks about twistors. We're not going to go into that at all. But again, we can think up of any sort of mathematical field. These are fields. These are mathematical fields that sort of come out of our imagination, and we're generalizing them as best as we can. And so we can talk about how these fields, so we have fields, right? So I'm going to reiterate myself a bunch. So just to make sure that we've established these ideas as best as we can, we have these fields: scalar fields, vector fields, tensor fields, spinor fields, covector fields, and then we can make them complex, right? We could say that scalar fields that we're looking at are complex scalar fields. What does that mean? That means we're introducing complex numbers, right? So, again, this is our attempt to, our feeble attempt to generalize as best as we can, or as much as we can. So within the domain of scalar fields, our scalars can be complex. So they can be complex. We can also have octonionic scalar fields, right? So octonions are four-dimensional numbers. We can, as far as the mind can go, we can even talk about quaternions. I should have done that in reverse. Right, because quaternions, those are the four-dimensional ones. The octonions are the eight-dimensional ones, right? And the complex are the two-dimensional ones, and scalar are one-dimensional. These are all numbers, right? We're definitely not going to go into octonions. We might go a little bit into quaternions, depending on how much I tangent, but if I remember correctly, I don't think this book goes into octonions or quaternions. But it will go into complex scalar fields. So this is something that we're going to concern ourselves with later. Right, so now these are the actors that are involved. Right, so he has, still on page 35 here, these are the actors that are involved. He then wants to say, okay, where these actors, so they live in these fields, and each field has its own dynamic to it. its own unique dynamic to it, and it's going to depend. Those dynamics are going to depend on the differential equations that govern those dynamics. So we can have, for example, a Klein-Gordon equation that dictates the dynamics of the field, right? So the dynamics of the fields. And he calls these the rules for the free fields on the page. And a free field is really just a field. Again, we'll go into more depth on this later. But a free field is really just a field that doesn't have any interactions at play, right? So we don't have any self-interactions between fields. We don't have any anything interesting, basically, that's going to affect the dynamics of our fields. And there's going to be three ways we talk about these dynamics, or three different types of equations, if you will, that govern these dynamics. One is the Klein-Gordon equation, right? So Klein-Gordon equation is going to give us the dynamics for a free scalar field. Excuse me. We're also going to be able to talk about the Dirac equation. This is going to be a very important equation. Dirac equation. And then the Maxwell equation. Oops. Maxwell equation. And roughly speaking, our scalar fields are going to be assigned to our Klein-Gordon equation. So we're going to see that the dynamics for scalar fields are governed by our Klein-Gordon equation. Our dynamics for our spinor fields are going to be governed by our Dirac equation, and the dynamics for our vector fields are going to be governed by our Maxwell equations. And then we'll be able to talk about interacting fields, right? So these are free fields. Free FIE fields. And then the interacting fields. And so how are we going to be able to have these interact? Well, there's another diagram in the book somewhere. It's not on page 35. But if we have our scalar fields, our scalar fields can interact with our spinor fields. Or they can interact with, actually I want to maybe put this a little bit more off to the side here. So our spinor field, or scalar fields, can interact with our spinor fields, and they can also interact with our vector fields. And our vector fields can interact with our spinor fields, but yeah, so we can have this interaction also. So if our spinor field interacts with our vector field, so if our spinor field interacts with our vector field, these are what are going to be called gauge, are going to lead us to gauge interactions. So the interaction between spinor fields and vector fields are going to be gauge interactions. And our interactions between spinor fields and scalar fields are going to be called Yukawa interactions. So and we actually, I'm realizing right now that this arrow actually is not on page 35 here. And this is sort of this is gonna be the big chunk of the book, right? So without further ado, actually I think I might keep this a little bit short, this video a little bit short. But yeah, so so we have our we're gonna be able to talk about our free fields. We're gonna be able to talk about our interacting fields. And we always want to keep in mind that there's tons of different types of fields involved. We have scalar fields, vector fields, tensor fields, spinor fields, covector fields, twistor fields, octonionic or complex scalar fields. So many different types of fields. And these are all mathematical in their essence. Right? We can't see, feel, hear, or touch them, or smell them, or anything. We can merely write them down on our iPad or on our piece of paper and play with them in that way. And with that being said, let's go on to chapter 2, which is going to talk about space-time and the structure of space-time. We're going to be talking about 4 vectors. We're going to be talking about different types of transformations, Lorentz transformations, Poincare transformations. We're going to be talking about time dilation, and this is going to be pretty much a review of special relativity, but no, nothing will hurt in doing a review on this kind of stuff. And I don't know how I'm gonna break up this next chapter, because these chapters can be long. I don't really want these videos to linger on that long, but we'll see. Maybe we will have a chapter per video, and we'll just have these videos be like 2 or 3 hours long. Or maybe I'll find something else or maybe I'll divide the chapters up in half, or chop them up in thirds or something like that. But anyways, I look forward to seeing you in the next video. Bye.